Thanks very much, Simon, for the kind introduction. Just checking you can hear me okay. Still working.
Yep, sounds
Yeah.
good.
Okay, great. And thanks to everyone who's joined this seminar. Appreciate your time is precious. So hopefully you will enjoy it and we'll have some interesting discussions as well. So I'm going to be talking today about our work in what I've called battery systems engineering. This is because I'm an engineer. I'm not a materials scientist or a chemist. So my work on batteries, our work on batteries is very much focused on how we can squeeze more out of batteries that we have. Not so much on how we can build new types of batteries, although that is interesting and definitely part of our scope as well. But mainly we're interested in making batteries that we have perform better rather than building new batteries. So there'll be a theme throughout, and I'll be talking about various things we've done in the world of modeling and all the way through to estimation and control. I hope you enjoy it. Okay, so here's an outline of the talk. I'll give some context, some motivation, and just general background on our group. And then really the three main sections I want to dive into a bit more detail. The first one is on modeling, which I'll hopefully give you a bit of context for why I think it's important and how it can have an impact. And then towards the end of that, I'll talk about how we parameterize models, which is a really important challenge, I think. Second major topic is on degradation and lifetime. Again, I'll try to place that in context and then talk a bit about some of the work we've done. And then the final one is on control. So once we've got all this information, we've done some modeling, what do we do? What decisions do we make? What actions do we take? And again, I'll try and show some examples of how we can use this information to make batteries perform better. Okay. I'm sure this audience knows the context pretty well, so I'll just go through this quickly. But we know that lithium-ion demand is increasing rapidly. Cost has been dropping astronomical amounts by 97% from the mid-90s to just a few years ago, and it's continuing to sort of decrease. This has really caused an acceleration in the rollout of batteries, not just for consumer electronics as it was in the early days, but these days, obviously, for electric vehicles, grid storage, and so on. And this graph is quite interesting. These are just some projections, in this case, from Bloomberg. But you can see that a lot of that future demand is really still being driven by passenger EVs, okay? So bear that in mind. And then, obviously, one of the things that this then leads to is a lot of concern and research and development around where do the materials come from and how do we make the batteries last as long as possible and recycle at the end of life. I'm not going to talk about these topics today, but I just wanted to say that I think they are really, really important topics, and they're going to become more and more important as time goes on. So the bit where we fit in is maybe to say, okay, how can we extend the life as long as possible, and even know what it is going to be for a particular usage application. So what is systems engineering? I guess it's quite a broad topic within engineering, but from a batteries point of view, I suppose what we're trying to say is that we want to look after batteries better. Batteries are a bit like people. They don't want to be too hot. They're mechanically fragile, and unfortunately, they degrade over time. And so you could think of these kind of three areas, for example, as key places where the stuff you put around the battery, the thermal management system, the mechanical containment, and the usage electronics and sort of measurements and control systems can make a real difference between a system performing really well and not performing quite so well. So these are the kinds of topics that I'll be talking about. Just to give you a little bit of background on the situation that we have here in Oxford University, we're really lucky to have great heritage. This was the place where John Goodenough and team back in 1980 actually developed the lithium-ion cathode material. There's a plaque on a wall down the road that commemorates this. And if we fast forward to today, we have a huge number of faculty, postdocs, PhD students. We have academics spanning materials and maths, many names that I'm sure you know here on this list. And so we're really lucky that it's a real center of research in the UK. And in my group, we are interested in a variety of things, but mainly we're interested in modeling. We're interested in diagnosing health and performance from data. We do quite a bit of testing, mainly of lifetime, and then we are interested in how we control batteries to make them perform better. And this is just a photo from our spin-out company that Simon mentioned in the introduction, Brill Power, which builds highly modularized battery systems with a lot of active management of balancing and so on. And we've been lucky to have several successes in the last few years. I can't list them all, but I couldn't help listing a few of them if you'll indulge me for a minute. So this just shows some of the work that we've done. We've worked quite closely with industry. We had a PhD student, Ayrton, worked with Samsung in Korea. He built a very fast implementation of the Newman so-called P2D model, which was used by Samsung in Korea. We've done quite a lot of work with automotive companies on diagnostic techniques and testing. I mentioned Brill Power already. We've also done some work at a higher level, sort of up towards kind of policy and techno-economic stuff, working with the Faraday Institution and government here in the UK on the production side and thinking about gigafactories. And these days, thinking quite a lot about grid energy storage and the interaction between battery lifetime and revenue streams that we could get from grid storage. And we were very pleased to be involved with this large project just down the road from here in Oxford, which is a very large 50 megawatt hour transmission connected grid battery as part of Energy Super Hub Oxford. Okay, so hopefully that gives you at least 5 minutes of kind of background. And what I want to do now is just go through in a bit more detail some of the work that we've done in these three areas. So I'm going to start with modeling. I'm sure some of you know lots about modeling, but I just wanted to kind of paint a picture of the kinds of things that we can do with battery modeling. First of all, battery modeling covers a huge range of different scales. So we have research groups working at the atomistic level, all the way up through the kind of particle structure scale to the device level, and then the pack level, and finally at the sort of systems level. And this is both really exciting, but also a huge challenge because, as you can see, we have a massive range of time and length scales. So, you know, how do we stitch these different levels together is a key question. And I know many of us are actively working on that. In my particular group, we're interested in this kind of space. So I would say the devices to systems kind of level is where we're at. I am mainly from an electrical engineering background. We do quite a bit of sort of electrochemical modeling, but we have other colleagues such as my colleague Charles Monroe, who's very expert in fundamental electrochemistry. And then we have other colleagues who go down to this level as well. And then up on the right-hand side of this, I think interesting conversations around long-term investment decisions, circular economy, and that kind of thing as well. And modeling can help with all of these things. We can use modeling to get properties from structures. We can get performance from properties, and then eventually start making decisions around that. So to give you a few more examples of the impact of modeling in this kind of middle region, we could broadly think about it having an impact in three areas. The first one, I think, is design. So we could use models to, for example, predict the behavior of new chemistries. We could design electrodes. How thick or thin should they be? Where should the tabs be? We could look at heat production and so on. A big topic, certainly in industry, has been estimation. So this comes from the idea that really we can't measure many things in a battery. We can measure voltage, current, temperature. But what we want to know is things like state of charge. That's quite hard to get directly, and state of health, how big is the capacity of the battery, and so on and so forth. And ideally, we want to do this in situ, non-invasively, without interrupting normal operation. So estimation is a big part of model impact as well. And just to show an example of this, this is typically what's done actually by electrical engineers, control engineers. So in something like a battery management system, that's BMS, we would typically take a model. The model would, for example, take a measured current, predict a voltage, maybe a temperature, then we'd compare that to the actual voltage, get some kind of error, and we'd feed that back and use that kind of negative feedback to drive the model towards what we hope is the real world states. And here's just an example. This is a simulation. But you can see, for example, in this case, we were actually able to sort of track things like stoichiometry in the anode and so on. And so, yeah, if you're familiar with this, you'll know what I'm talking about. If you're not, hopefully that kind of gives you a flavor of how you could use a model to try and measure something like anode stoichiometry that you can't measure directly. And then the final layer, this control layer, how is modeling useful? Well, we can do things like, how do we optimally fast charge a vehicle, or how do we optimally charge and discharge a grid storage system to make revenue whilst also not aging the battery too much? We can predict lifetime, which is important for warranties and so on. We can understand integration issues such as losses and voltage ranges and so on and so forth. And there's many other things that are not mentioned in this slide, but I just wanted to give you a feel for some of the areas where modeling makes an impact. One of the things that I think is important for me to say, and you know, I hope many of us appreciate this, but there isn't a single model which solves all of your problems. I think sometimes in the literature in this space, I see people write things like, oh, the Newman model, the P2D model is more accurate than a circuit model or whatever. That may be so, but actually, I think I'd flip it around and say there are different models for different purposes, and it depends what you want to do. So this picture is a very complicated sort of picture, but I'll try and talk you through it. So on the left-hand side, we have a bunch of example models, which are basically electrical models of batteries. The very simple one is just a voltage source and a resistor. And then we can step up through adding different components and so on. And then if we jump across to the central region, we're talking here more about electrochemical models based typically on porous electrode theory. But again, there is no such thing as like the one electrochemical model. In fact, we could think of a whole family of different approaches where, in this case, if we go from right to left, we're increasing the macro scale complexity. So, for example, if we have a large pouch cell, we might be interested in this left-hand column where there'll be temperature variations, you know, from one corner to the other. Whereas if we're just modeling a coin cell, maybe the right-hand column would be sufficient. And then the sort of y-axis here is the microscale complexity. So that's saying, do I actually need to know the whole microstructure, for example, this top row, or can I just treat the microstructure as a sort of uniform representative particle, which is what the bottom row is doing. In fact, the bottom row, even ignores the particle and just treats it as like a zero-dimensional point. And so within this kind of whole family of models, we see some familiar faces. So the so-called DFN or P2D or Newman model is this one sitting here, and the single particle model is this one sitting here. And I think what's noteworthy about this is that both of these are on the bottom right end of this picture. So these are actually on the simpler end of things in terms of complexity. And people get uptight about the fact that electrochemical models and circuit models are different, but actually I don't think they're very different to each other. I think the key difference between, say, this model here and you know, the SPM, for example, is that you're modeling two electrodes separately. There's a diffusion PD in there, and maybe the properties are a bit more physical if you're lucky. But actually, I think this model here is reasonably close to some of the stuff in this bottom right corner. So if you're interested in playing with models, if you're new to modeling, or you just want to have a go, I would encourage you to have a look at this website, pyban.org. This is open source software. It's well documented, and you can run some of it directly in the browser. So go and have a look at that. One of the things I like to keep in the back of my mind, it's easy to get sucked down the rabbit hole of modeling, but actually, we should remember that most electrochemical devices, on a very basic level, we can think of them as a voltage source and a resistor. The voltage source, if you like, is representing the thermodynamics, and the resistor is representing all the losses. And this framework, although very simplistic, it actually maps quite well to different devices. So, for example, these I won't go through these in detail, but you know, for a supercapacitor, fuel cell, etc., the voltage source is defined like through these equations. In some cases, it varies with state of charge for a battery, for example. fuel cell, the thermodynamic voltage is basically fixed, ignoring pressure and temperature variations. And then the resistance, if you like, represents all of the other stuff that causes a voltage drop when we start to pull current. And, you know, battery is a good example. Here we've got ohmic losses or ionic, and then kinetics, the reaction, and then some diffusion-related stuff. So you might be thinking, oh, it's way too simple, but actually, let me try and convince you that it's a good starting point, at least. In a good battery, so if we take like a well-designed commercial cell that is matched to the application that you have chosen, I would argue that the open circuit voltage should be much larger than the overpotentials, right? We don't want the voltage drop across this resistor to be huge, because that's going to generate a lot of heat and so on and so forth. So in a good battery, this should dominate. And what that tells me is that basically understanding the open circuit voltage and modeling it really well is absolutely crucially important for battery modeling. All of that complicated stuff on the previous slide is really, give or take, is really about this resistor. It's modeling this in a more complicated way. Now, if we care about things like heating and temperature distribution and degradation, then of course we need to worry about that. But let's not lose the wood for the trees, as we say. The open circuit voltage is critical. And actually, if we just care about a very simple electrical model of behavior, this model is quite good, right? So here's an equation which has OCV, one from each half cell. Then we've got overpotentials and then some additional ohmic drops. We can kind of simplify it slightly. If we group the electrodes, linearize the overpotentials, then we just get voltage source and a resistor. And if we look at some measured data, you know, this is a current pulse, and I apologize, the x-axis here is a bit of a mess, but it's about 500 seconds. So we have a pulse in current from 0 to 1. And this is a real battery. And you can see the voltage is nice and stable. Then it drops instantaneously, which is this IR term. And then there's a slight curvature, and then it kind of drops gradually, which is caused by the SSC change. So the only thing that's really missing in this model is this slight curvature effect here, which relates to transport. But otherwise, we're capturing a lot of the main features quite well. Okay. So at this point, I want to just take a quick aside to say, I think there are still lots of interesting issues in modeling to be worked on, and important issues. I've just mentioned how OCV is critical. One of the things that really messes up OCV, if you like, from a systems point of view, is voltage hysteresis. And so this is the first important issue. Voltage hysteresis is key. It's more evident in some materials. Here's an example of measurements from a lithium iron phosphate, graphite cell. This is OCV. And you can see, first of all, that there's a significant voltage gap between charge and discharge. These are slow charge discharge measurements. But then also interesting things happen. So if we go to sort of the low state of charge region and do a small charge discharge just around 20%, we get this orange shape. We do the same at 50%, we get this purple one. Do the same at 80%, we get this green one. And you can see that the shapes of these things are slightly different to each other, and they don't quite reach, in this case, the blue curve at the top. So there's definitely like interesting and strange things going on with hysteresis that we're still trying to understand in our group and as a community. And just as a side point, the way that we measure this is critical. This just shows difference between GITT measurements, where we let the voltage relax for a long period of time, versus very low current, sort of C by 24 or lower measurements. And you can see that the size of the hysteresis gap is different between these two. So, you know, this is kind of a side issue, but something that we need to think about. But this is not just an issue with LFP, right? Here we've got some data at different temperatures from an NMC positive electrode, graphite negative, and then this is the cell at the bottom. And you can see that there's hysteresis here too. It's slightly more prevalent at low temperature. And this sort of mainly relates to the graphite, okay? Now, there's discussions we could have about what's causing that, and is it so-called dissipative or not dissipative hysteresis. But from a practical point of view, you're definitely going to see this on the kinds of timescales that battery management systems care about. And so putting these into models is important. And I know Greg Plett has done lots of nice work on that. Yeah, if you're interested, go and have a look at what he's done. In our group, we're doing experiments and modeling around this stuff at the moment. So that's important issue number one. Important issue number two is that I mentioned earlier that people, in my opinion, are maybe too obsessed with the P2D model as the end of the road. Maybe all of the P2D model emphasis on local transport across the cell is a red herring in some situations. And I want to suggest to you that one situation where it might be more important to look at something else is when you have a large format pouch cell. So here's a 20 amp hour pouch cell. In this situation, we need to worry, I would say, about macro temperature variation. So here we know that the temperature uniformity from like this corner to here is really, really important, and might be more important than modeling the electrolyte transport, for example. And we've done some work. This has really been led by my colleague Charles Monroe, but we've done some work where we do pulses of charging and discharging of these cells, and then look at the resulting temperature profile with an infrared camera. So you can see these kind of pulses are like tens of seconds, charge, discharge, charge, discharge. What that does is it heats the cell up to a steady state, and you get these wiggles related to entropy. And then we've done quite a bit of modeling of this setup using kind of coupled simplified electrochemical thermal models. And then we fitted those models to experimental data, and you can see can get pretty good fits. And you can see that what happens is you get this hot spot kind of forming towards the tabs, which gradually moves down. And you can also see the kind of breathing effect as the cell charges and discharges related to the entropy term. So this is pulsing at 4C with 100-second pulses at 30% SOC. So what does this kind of exercise tell us? It's quite interesting. I think it tells us a number of different things. The first thing we learn is that in this particular case, a large-scale measurement like the surface temperature under these experimental conditions using a thermal camera, actually the shape of that measurement relates strongly to our assumptions about diffusion in the solid. So we can play around from a modeling point of view with the diffusion time, and in this case, you can see a huge range of different orders of magnitude of diffusion time, and you can create different horizontal kind of curvature in the temperature that you can see with a camera, depending on that assumption. And so we use that to then do inverse modeling from a number of these different pulse experiments and come up with quite plausible values just from fitting for things like exchange current density, ionic conductivity, and so on. And many of these values, actually, they are relatively fixed with respect to state of charge. So there's some things that change, obviously, entropy and OCP change, but many of these values are kind of fixed. So we're relatively confident that we're getting something fairly reliable. And in order to check that, we actually took values, put them into a separate validation test where we discharge a cell fully from 100 to 0, rather than just pulsing around an SOC. And we can get very good voltage and temperature matches between the model and the experiment in this situation. So macro temperature variations are important, particularly in larger cells, and maybe something we should be focusing on a bit more using simplified electrochemical models. Okay, the next topic I want to talk about, just to bring us into the end of this section on modeling, thanks for sticking with me, is this need to parameterize models in general. And one of the things I think is an active area of research in many groups around the world, including ours, is building tools to help parameterize models. This can be done in a couple of different ways. We can either rip batteries apart and measure stuff, or we can take data from full cells and try and fit it with models. And in practice, we'll probably do a combination of both of those two things. But in our group, we've been working more on the second one. So that's kind of the top-down approach, where we do measurements on full cells and then try and fit models to them, like I showed in the previous slide. And just in case you're interested, we are developing a tool called PyBot, which is Python battery optimization and parameterization. You can go to the GitHub and learn about it here. It's all open source. But this is a tool which takes a forward model, such as a model from PyBAM. It could be a circuit model. It could be a more complicated electrochemical model. And then it runs a parameterization loop where it takes some data, runs it through the model, measures the output of the model, compares that to the measured data through some kind of cost function, and then uses an optimizer to basically tweak the parameter values of the model to try and get the model to fit the data. And the beauty of this, I mean, this, by the way, is a well-known thing within control engineering. It's called system identification. We're not claiming to kind of have invented it, but the beauty of this is we've got a very flexible framework for trying lots of different models, lots of different optimizers, lots of different cost functions. And just to show you some of the things that you could do, a couple of examples. So one is parameterizing model parameters. In this case, it's kind of a toy example, but we're just fitting a discharge curve. So we add some noise to the discharge curve, and then we want to estimate two parameters, so the negative particle diffusivity and the contact resistance, using the single particle model. And you can see here, we can plot like a cost function by brute force, showing that there's a kind of sweet spot where you get the best fit between the model and the data. This allows you to visualize that and then try out lots of different approaches to finding the cost function. You can even try different cost functions if you want, which is what's shown on the right. But perhaps excitingly, we realized if you're building a tool that allows you to fit models to data, you can also tweak parameters for design objectives by changing the cost function. So say instead of I want the model to fit the data, the cost function becomes maximize the energy density at 1C. And so here's an example where we take the single particle model with electrolyte, SPME, constant 1C discharge, and we want to optimize the gravimetric energy density by changing some geometric parameters. And in this case, we actually have 4 geometric parameters. So we say that we are allowed to change the electrode thicknesses plus the active material volume fraction and a representative particle radius. Sorry, 5 parameters, 6. The 2 second ones come in pairs. And what we see, it becomes hard to obviously to visualize once we have 6 things changing, but you can sort of slice through the landscape. And what you can see is that there's always a kind of Goldilocks region, if you like, where there's a sweet spot where the combinations of parameters really works in this particular case for a 1C discharge. And interestingly, we also get insights into why it doesn't work when it doesn't work. So for example, up here, maybe there's transport limitations, and over here, maybe the electrodes are unbalanced with respect to each other. So I think, this is a really exciting new area to look at. Okay, side point about impedance. We've done a lot of work on impedance. Don't have a huge amount of time to go into it, but I think it's a really cool tool for parameterizing models efficiently. And just to give you an example from some work a few years ago, so this is the use of EIS data at low frequency. So we're actually going from about 1 hertz down to microhertz to estimate diffusion timescales. So that's like R squared over D. What you can see here is there's a very strong interaction between how easy it is to estimate the diffusion time and what the OCP slope is doing. That's one of the things we really learned in this work. So, for example, if we have an appreciable gradient in the OCP in the positive electrode, then we can identify the positive electrode diffusion time really nicely at this particular SOC, right? Because if we wiggle the current, we wiggle the voltage, and what we're mainly seeing here is a wiggle in the surface concentration at the positive electrode because the negative one is quite flat. Whereas in the negative electrode, you can see that there's like a valley in the cost function landscape. And flipping to this side here, we see that both electrode OCP slopes have appreciable gradients. So we get a sort of more of a bowl shape, if you like. But we have a real problem in the middle region, right? Because the OCPs, by the way, these are these are reference electrode measurements. So that the full cell data is this blue solid curve, and then the positive electrode is the top one, the dashed one, and the bottom one is the graphite. And so you see in this middle region at 50% DOD, because the OCP slope is very shallow, it's actually very, very difficult to get the diffusion timescales using these voltage measurements, which is kind of logical with hindsight, but it was something I think we learned through that paper. And at the moment, we're doing lots of work on new kind of extensions to normal EIS. One area of interest is so-called non-stationary EIS. This is where the system is actually traveling, say, in temperature and SOC, and we want to extract the whole family of curves with one set of measurements. And the other one is nonlinear EIS. So this is where we inject a high amplitude sinusoid and we excite harmonics. And then these harmonics help us to identify parameters better in models. Yeah, the real expert on this is Noel Hallemans. So do look up his work if you're interested in this topic. Okay, so that's modeling. Next two sections are a little bit shorter, just to set you at rest. So I'm going to talk a bit about lifetime and then control. Lifetime is important. I think we'll appreciate this, but let's just ground it in some reality. So if you're an electric car owner, you want to know how long is your car going to last? How much will it be worth in 5 years' time? Should you sell it before the warranty runs out, for example? If you're investing in a large battery project, you want to know what the return on investment is. If you're doing maintenance on off-grid systems, you need to know how many spares to order. So lifetime modeling is important for these kinds of reasons. And unfortunately, degradation of batteries is a complex topic. We know that it depends a lot on how you use the batteries, and it's hard to generalize, but to give us a flavor, we know, for example, that higher depths of discharge tend to age batteries more. That's these cells which are aging more in this work are higher depths of discharge. Time at highest state of charge also makes a big difference. In this case, this is a model, but the SEI thickness growth rate is much higher if we hold the cell at higher voltage range, for example. A particular issue that's been talked about, including in this paper on knee points, is this idea that there would be an acceleration of the capacity failover curve in later life. So everything's fine at the beginning, we degrade reasonably kind of shallow curve, but then something happens later on and the battery starts to drop off a cliff. And this has been shown in quite a few data sets, but I think there's still quite a lot of research to be done to understand why is this happening, what particular interactions of complex pathways are causing it. And there's lots of things that can interact, which are shown in this picture here, which lead to knee points. So that's an important area of research. If we think about the lifetime challenge in general, I think it's kind of a two-level problem. So the first level is diagnosing what the health of a battery is in a real application. It's difficult to measure. To do a full measurement, you basically have to fully charge and discharge the system. That's not always practical. So knowing just where we are now, that's a challenge. And then the other part of the problem is lifetime modeling, predicting what is the lifetime going to do in the future, given a certain set of assumptions about usage. And from that, we can start making decisions. So let's talk a little bit about both of those. So first of all, let's talk about lifetime modeling. There are a number of ways of doing this with physical models, electrochemical models, the kind of DFN stuff that I talked about a few slides ago. The basic idea here is that we would take something like a simplified electrochemical model. This is just an example showing a single slice through a single layer in an 18650 cell. And then we would say hypothesize a mechanism for degradation. It can be whatever you like. A popular one, for example, is solvent diffusion and then SEI growth. And then you can work out what the equations for that are, implement them in a tool like PyBAM, and build a kind of virtual battery cycler and see how this is going to degrade under different situations. Challenges with that are, where do we get the parameters from? Do we actually understand what's going on? And there are many more, and so on and so forth. And I think in later life, also other things, interactions of different mechanisms is a really tricky problem. So some people, including us, have said, okay, well, that's very hard. Maybe we can just use data and do sort of data-driven modeling. And we've used, in our group, we've used sort of data-driven approaches, machine learning approaches for some years, both to do diagnostics, that's health estimation now, and prediction of future life. So for example, there's some papers here about this where you just take a few voltage measurements and then come up with a capacity estimate, and then some other papers where we predict future life based on correlations between capacity fade. But I think a big challenge with this is that we don't really have rich enough data sets. To generalize, you need not just large data sets so you can deal with cell-to-cell variability, but rich enough data sets, because so many things can change: temperatures, SOC ranges, chemistries, and so on and so forth. If you take a model, train it on some data, such as this blue curve, and then predict it on a different test condition, maybe different application, you're probably not going to get a good result. And so we need this kind of richness of data. We need more data. And I think if you're working on experiments, please release the data so that we can all see it. And maybe field data can help. And we've done some work on this. And I just want to show you for a couple of slides what we've done with field data. So we've done some work on using data from off-grid solar systems, mainly in sub-Saharan Africa, where we have measurements of voltage, current, and temperature. And we've worked closely with a company who have actually a lot of lead-acid battery systems in the field and are gradually switching to lithium iron phosphate. But we've taken a method which is based on this very simple idea of treating a battery like a voltage source and a resistor, and then trying to estimate the capacity and the resistance changes over time with some machine learning techniques, which I won't go into detail, but the basic one we use is called Gaussian process regression. And this is essentially a sophisticated way of smoothing the data and calibrating for things like temperature and so on. But in this work, we dealt with both sides of this problem. So how do we diagnose what the health is? And then how do we predict the future life? The diagnostic problem is essentially a noise and smoothing problem, and the prognostics problem is essentially building a model that says, given some set of aging factors and inputs, the battery is good or bad. And in this case, we used a classifier to do that. And just to show you some results, so for the smoothing problem, we can see here voltage measurements over a couple of years, and we can see resistance functions which are learned from this simple model. But this is like a four-dimensional resistance function, which is a function of state of charge, current, temperature, and time. And by learning this function of these four things, we can then calibrate it to say, I only want to know what the resistance is at a given set of conditions, so a given current, a given temperature. And if we don't do this, we know because the resistance is strongly impacted by changes in temperature, changes in current, and so on, this is going to look very noisy if we try and use it as a health metric, unless we do this calibration. So we did this work where we did this on 1,000 batteries. And so you can see some of the resistance trajectories that we extracted from the field. These have all been calibrated now. We combine these with some features that we basically extract directly from the data, such as calendar age, charge throughput since the beginning of life, mean temperature since the beginning of life. And then in this case, the company has labels. So systems get taken to a workshop if they fail. And so we could separately train a classifier to say this system has been independently tested and has failed or not. And so we were able to therefore build a kind of life model that can predict whether a system is going to fail or not up to about 2 months in advance. So this graph here shows the accuracy of that prediction under different assumptions. And in the best case scenario, it's about 85%. So it's not perfect. 50% here is flipping a coin, but it's about 20% higher than the benchmark, which doesn't do this kind of calibration step that I talked about earlier. The cool thing about this is, we can give some useful information to an end user to say, look, the probability of failure on these 23 batteries is high, and then they can get the right stock in to order. But secondly, we also get an aging model out of this process. So we can look at what the classifier thinks is important. And we can see, for example, in this data that obviously the resistance, which we fed in as an input, is important, but also the mean temperature, the mean voltage are key factors impacting the life. I'll come back to that a little bit later. We are currently working on rolling this out to lithium-ion systems. This is just some example using NCA data. And you can see that in this case, we can use this approach to predict capacity and resistance. And we also get, in this case, fits of the resistance as a function of SSC and age, and also circuit parameters in an RC circuit model. Okay. That was a lot of information. I hope you're still with me. For the last 10 minutes or so, I just wanted to answer the question, which is, so what, right? So we've talked about modeling, we've talked about degradation, but what can we do to take action once we have insight into how well or badly a battery is performing? And so To me, this is really exciting because this is where we can start to actually show real world benefits. So I'm going to talk about control. And just to give you a big picture on where this could go, right? If everyone could work together, if there was enough open data, if manufacturers had enough data, we could imagine a situation where a battery manufacturer tracks data all the way through from components to systems that they build, pack diagnostics, BMS, and so on, all the way through applications to end of life and recycling, and then is able to basically use later life kind of performance to influence earlier decisions. And obviously, there are lots of challenges with this vision. You know, this is happening hopefully 10, 15, 20, 25 years later than the cell was made. And by that stage, the technology has moved on. But you can imagine kind of smaller feedback loops within this. And that's what I want to show you now. So here's a simpler example. One of the things we can do is just to adjust the way that the battery management system controls the voltage limits that it goes to in order to extend life. So, for example, in off-grid solar home systems, we have seen from the data that we've analyzed that there are high users who use more energy, there are moderate users, and there are infrequent or systems which are turned off. And in all of these cases, these systems are generally a bit oversized, right? So the battery capacity is larger than most people need, even the high use case. And so there's basically different degradation rates are experienced by different use cases. This is, by the way, this is lead acid, but the same logic applies to lithium-ion systems, and I'll show you an example. So if we could basically adjust the way that users use the battery without impacting the usage, so they don't really see the adjustment, then we can extend the life. And in this case, because in lead acid systems, you always want to stay at high state of charge to avoid sulfation. They tend to sit on float charge, which means that the voltage in the SOC is in the high range. But if you were to allow the voltage and SOC range to be wider, it could significantly extend the life. And we're currently working with a company called Bbox to try and do some in situ field testing to see if this is actually possible in real systems. A very similar logic applies with LFP systems. I have a home battery. I have solar panels on my house. My home battery, at the moment, in the software, it doesn't give me a way to control the upper state of charge limit, which unfortunately means in the summer, the sun comes out, the system charges up to 100% by maybe midday, and then it sits at 100% until 6, 7, 8 p.m. It would be great if I could just tell the system, like, lower the upper voltage limit, lower the upper SOC limit for the summer. Or even better, adaptively change the SOC limits according to the usage and the weather forecast. And this, I think, could significantly impact life because we know that LFP systems degrade more quickly at high voltage. So here's a slightly more complicated example of this. If you have a large grid battery system, what you typically want to do, there's different ways you can use it, but one way you can use it is something called energy arbitrage. What this means is that there's a price signal, maybe varying in time. Maybe you wouldn't see this at the residential level, but you would see this if you were a larger scale business user. Although we do have residential variable prices in the UK. So what you want to do is charge the battery when the price is low, and then discharge it when the price is higher. And you will make the profit based on the price difference between charge and discharge. But when we do this, we need to do it in such a way that we make more profit than the cost of using the battery to do that cycle. And so there's an aging model that has to sit somewhere there. And a very simple example of this is solar self-consumption. Here is a photo of me on the roof where my solar panels were installed on a not very sunny day in the middle of winter, but it does work. And here's a battery that we've got at home. And I have lower electricity prices at night than during the day. And I also have kind of free, if you like, electricity from the solar panels. So I want to make sure that I charge as much as possible from solar and then discharge when I have loads. And that's actually how most home energy storage systems are configured. But if we had full control over the charge and discharge, then we get a very different strategy depending on whether we include aging or not. So if we don't include aging, then we get potentially a strategy that says we should charge and discharge the battery very aggressively, right? So that's what this light blue signal is showing. Whenever there's a small fluctuation in price, it's sort of doing charge, discharge, charge, discharge. But if we, that's going to age the battery really quickly. So what we need to do is bring in some kind of lifetime model. And then in this case, it's a very simple model, but it basically reduces the number of cycles per day that we're doing. So this is just a toy example, but obviously it can become a lot more complicated. So the typical way in which this is done by companies, I should say, many companies working in this space, is to formulate a kind of optimization problem where you basically say, minimize or maximize some cost function based on energy prices, the power of the battery for each 5-minute, 15 or half-hour time slot, and then the amount of time, subject to some costs. And this is the cost of aging. And there's a whole interesting amount of research to be done on how exactly we capture this cost of aging. I don't have time to go into that, but I'd love to chat to you about it if you're interested. Somehow we also need to account for the fact that the battery has a finite power level, has a finite energy level. And so we need some kind of model, which could be as simple as saying it's like a bucket for energy. But if we do this, we can run these optimizations with different assumptions and see what happens. And we did this a few years ago. We actually used data from about 10 years. This is a slightly older project, but we used data from Belgium in 2014. You can see in this data, interestingly, how the price of wholesale electricity changes with season. You can see the summer holidays in the middle as well. And we ran these optimizations against 3 different modeling assumptions. And I realize this is a complicated graph, but I just want to point out a couple of interesting things. So the case on the left is we don't care about degradation. We have a simple model, we don't care about degradation. Case in the middle is we have a simple model, but we have a fixed cost per cycle. And the case on the right is we have a single particle model which knows about voltage. It knows that if the battery sits at higher voltage, that's bad. And you run these optimizations against a whole year of data. So this shows the day of the year and the hour of the day and the power in and out of the battery. You can see that for the very simple model, we get something quite similar to what I showed here. So basically very rapidly fluctuating charge-discharge. And you can see the battery spends a lot of its time at either high power charge or discharge at either high voltage or low voltage, full or empty, and it's either charging or discharging in between. If we penalize the cost per cycle, then we get a very similar result actually to this. It's just sort of everything is shrunk inwards. So we spend still quite a lot of time at high voltage, slightly higher than low voltage, but we also have less power. So we kind of pull everything inwards, but we're sort of following the same strategy as this, just less aggressively. But what's really interesting is this kind of physics-based model, which knows about diffusion, it knows about voltage limits, it approaches voltage limits more gradually. It knows that if I sit at high voltage, that's bad. You can see it has a much more complicated kind of signal in terms of where it spends time charging and discharging. It spends much more time at low voltage because that's less degrading, and it has more kind of complex aging pathways. So we were quite intrigued by this idea. Does this make a difference, or is this just kind of maths? And so we took these 3 situations. We had a whole year of optimized data, and we said, let's test it on some real batteries. And so we took 2 cells for each of those 3 conditions. So we had 6 cells. We had the voltage and current for the whole year, and we fed it into a battery tester. And results, I think, quite interesting. So we plot revenue we would have made, okay, bearing in mind it's just one battery, versus lost capacity. We see that in the case where we don't care about degradation, we make a lot of revenue, but we also kill the battery quite fast. We lose 15% capacity. But in the other 2 cases, we have the case where we have a simple model, but we penalize the cost of each cycle. We lose kind of 3% capacity. We make not very much money. But the interesting case is this yellow one, where this is the sort of more complicated physicsy model. So basically, we're on a different gradient. We're making more money for each percent of lost capacity than we were in this case. And I think it comes out even more clearly when we plot capacity fade versus full equivalent cycles. Because here we can see that if we just penalize the cost of each cycle, that's the red curve, we're still following the same trajectory as the blue curve, which was the no aging model. But now with this more sophisticated model, we're actually following a completely different aging trajectory. So we thought this was quite a surprising result because, well, A, it worked, and B, these quite complicated models might actually have some connection to reality. So I found that was quite interesting. Our conclusions from this work were that, yeah, if you just throttle back on cycling, do less cycling, it doesn't necessarily change the trajectory. You actually have to think about the impact of sitting at a certain voltage or a certain temperature. And simple models, very simple models, leave a lot of economic value behind. The problem with this is it's actually really hard to implement this practically because it requires a very tight coordination between the battery management system and the energy management system. It becomes a real-time control problem. And often these are, in a real battery, the BMS is made by a totally different company to the EMS. You know, there's a kind of, you need some vertical integration to make this work. Okay, I think you'll be pleased to know that I am basically done. I just wanted to summarize for a couple of slides. So thank you for listening. So quick summary. So I've talked about systems engineering. We're trying to squeeze more out of batteries. This goes complementary with making better batteries, of course. Talked about battery modeling, how it can support design, estimation, control. There's a huge variety of different models we can choose from, and there is no one perfect model. We just have to choose the right model for the goal. Parameterization is challenging, is an active area of research, something that I'm personally very interested in. And if you want to have a go at modeling and or parameterization, have a look for PyBAM and PyBOP. Lifetime is also really interesting. It impacts warranties, it impacts maintenance investment. We need to diagnose health and predict life. Data-driven methods are great, but I think the issue is not so much like which exact machine learning algorithm do I use. It's much more about whether I have the data. And ultimately, all of this should lead, I hope, to lower costs and yeah, longer life for batteries. And I should just say a huge thank you to my entire research group, many of whom are in this photo, although it's a couple of years old, and also all of our funders. And a huge thank you to Simon. I'm involved in a couple of projects with Simon. And so much of this work is also with many collaborators, many more than I could name. But thank you to all of you for listening. And I'd be delighted to hear your questions.